This is an AS Further Mechanics 1 question on work and energy. Figure 1 shows a ramp inclined at an angle theta to horizontal where sine theta is equal to 2/7. A parcel of mass 4 kg is projected with speed 5 meters per second from a point A on the ramp. The parcel moves up a line of greatest slope of the ramp and first comes to instantaneous rest at the point B where AB is 2.5 meters. The parcel is modelled as a particle. The total resistance to the motion of the parcel from the non-gravitational forces is modelled as a constant force of magnitude R newtons. Part A used the work energy principle to show that R is equal to 8.8. Now the way I'm going to do this question is by calculating the total energy at the start, subtracting any work done against friction, and that will give me the energy at the end. That is the work energy principle, so no SUVAT here, just kinetic energy and potential energy. Now for our start energy, we have kinetic energy because it's projected initially with a speed of 5 meters per second. So using half mv squared, so half m, which is 4, and then v squared, which is going to be 5 squared. So that's 50 joules. Now in terms of potential energy, I'm going to call this point here the line of zero potential energy. So there's going to be no kinetic energy at the start. So PE I'll just make equal to 0. Then I'm going to look at the work done against friction. So work done against friction. So this is going to be any energy that I lose, and that's just going to be the resistive force times by the distance, the frictional force times by the distance. That frictional force is R and the distance is 2.5. So the work done against friction is just going to be 2.5 R. And then I want to work out my end energy, or the energy at the end. So again, I want to look at kinetic energy and potential energy. Now it comes to rest up here, so the velocity is going to be 0, which means that half mv squared is going to be 0. So the kinetic energy is going to be 0. And then we'll look at the potential energy. So for the potential energy, we need to see how much height has been gained. So I need to work out what vertical height increase there's been, and this is just going to be a little bit of trigonometry. So I'm just going to draw a triangle up here. I'm trying to find this distance here, which is the height that it's increased, the vertical height. I know that this is 2.5 and this angle is theta, and I know that sine theta is equal to 2/7. So I know that sine theta is going to be equal to the opposite over the hypotenuse. So that's going to be h over 2.5. But I also know that sine theta is equal to 2/7. So I can use this here by cross multiplying, for example, to work out what h is. So I'll have 7h is equal to 5. So the exact value of h is going to be 5/7. So the gain in potential energy, which is going to be the potential energy I have at the end, is mgh. So that's m, g, and then h, which is 5/7. So now I can write my work energy principle equation out, which is going to be 50 total energy at the start minus the energy that I lose, which is 2.5 R, will give me the energy at the end. And let's actually work this out. 4 times by 9.8 times by 5/7. Let's see if we get an exact answer. Yes, we do. We get 28 here. And this is just a matter now of rearranging to find R. So I could say that 2.5 R is going to be equal to 50 minus 28. So R is going to be equal to, let's see, 50 minus 28 is 22. So 22 divided by 2.5. And let's see what we get. 22 divided by 2.5. I get 44 over 8. Oh, sorry, 44 over 5, which is 8.8 as required. After coming to instantaneous rest at B, the parcel slides back down the ramp. The total resistance to the motion of the particle is modelled as a constant force of magnitude 8.8 newtons. Part B, find the speed of the parcel at the instant it returns to A. So we have at B, it basically slides down from rest, so that velocity is 0. At A, its velocity is V, which we want to find, and it doesn't say anything about using the work energy principle, so I guess it is, if you can solve this using SUVAT, you can do, but it's probably easier doing the work energy principle here. So let's look at the energy at the start, our start energy. Now, since it's released from rest here at B, that means that there's no kinetic energy, so kinetic energy is 0. For potential energy, we have worked out before, but just as a reminder, that's going to be M, G, and H. We worked that out to be 5 over 7, and so that's going to be 28. So energy at the start is 28. Work done against friction, well, that's going to be our frictional force times by the distance of that frictional force. So the frictional force, its size is 8.8 and the distance is 2.5. So that's going to be 22 joules of energy lost. So how much does that give us at the end? Our end energy, well, just like before, this point at the bottom here at B, we're going to call 0 potential energy. So potential energy is going to be 0. PE is equal to 0. And then kinetic energy is going to be half m v squared, and that is just v squared because we're just trying to find v, so that would be 2v squared. So now we can write our equation, which is the energy at the start, which is 28 joules, minus the energy that we lose, which is 22 joules, is equal to the energy at the end, which is 2v squared. So from here we can solve 28 minus 22 is 6, so we've got 2v squared is equal to 6. We have v squared is equal to 3. So v is going to be equal to the square root of v. Now we can't give our answer as root 3, that is exact, and we must give answer to 2 or 3 significant figures because of the use of g here in our working. So let's work that out. Square root of 3, SD button, I get 1.7320 and so on. But as I said, answer to 2 or 3 significant figures, so we'll put the answer up here. So you can give your answer as either 2 significant figures, 1.7 meters per second, or v is equal to 1.73 meters per second, but no more accuracy than that, otherwise you will lose a mark. And part C, we want to suggest 2 improvements that could be made to the model. Now, you'd want both of these because this original question, I think, was worth 2 marks. So we want to use a variable resistance. Now, I've got that from the fact that just before part A and part B, it talks about that the resistance of motion of particles is modelled as a constant force. And in reality, resistance isn't going to be constant. It may change as its velocity changes. So you might say something like have its resistance proportional to its velocity, something like that. But it relates to the this resistance being modelled as a constant force. We want to use variable resistance. And the second improvement would be to say not model the parcel as a particle, and that's because in part A it talks about the parcel being modelled as a particle. So for this, you may have something else written, like that you might want to include the fact that the particle might be spinning or rotating as it goes down the slope. That means we're not modelling it as a particle. Or that we might want to consider the size or the dimensions of the parcel. That also means that you're not modelling it as a particle, because a particle, we're saying, has no dimension, it only has mass. But obviously with parcels, the bigger the parcel, we're going to get different values for our answers in terms of the velocity for the type of the parcel. You could even talk about the packaging that the parcel is in, because that will change its resistance, variable resistance, maybe based on the packaging.